Welcome. In the previous lesson, you got to find out how fun and practical angular momentum was. Right? It helps us balance on bicycles. It helps us throw spiral footballs. It helps in a lot of practical applications like with stability and so on. Today, we're going to see how useful it is to problem solving. Let's get started. We're going to look at this new concept of angular momentum and problem solving by tackling a familiar problem which you see on the screen, which I've referred to sometimes as a modified Atwood's machine. So you have two blocks that are connected by a string through a pulley, and in this case it's not apparent which block is bigger, but we're actually moving upward. Okay, like that, M1 is moving upward and M2 sliding down the ramp. So the old way, right, the good old days, let's reminisce back when things were so much simpler. Okay, you see I've written F equals MA for both blocks, and we assume in the old way that the tension is the same throughout. Now we actually don't assume that the tension is the same. What we really assume is that the pulley is massless and therefore requires no torque. Assume that, then the consequence of that is that the tension can be the same in the ropes. Okay? So when you apply these two equations, right, you've got two equations and you have to solve them together. Right, now it looks something like this. And you can solve for the acceleration of the two-block system. Okay? In conjunction with this, you were introduced to a system approach where you look at these two blocks sort of as one object, since they kind of move as one. And when you take that approach, right, what we call the system approach, you saw that you could solve this problem more simply. Right? You could cut out the middleman, so to speak. You could ignore tension because the tension is a force internal to the system of the two blocks. And you could just look at this in terms of the forces that were external to the system, which were twofold in this case, right? There's the weight down here, okay, on M1, and then there's the component of weight down the ramp here, M2, right, M2G sine theta. So we had M1G and M2G sine theta. We just combine those, and you can see that we end up getting the same result either way, which is useful. And we can verify that these are both valid approaches. Okay, that was the good old days, right? That's what you came into this class knowing how to do. Recently, you were introduced to the new way. Let's take a look at that on the next screen. In the new way, you see now I added I and R to the pulley. We no longer ignore the mass of the pulley. Therefore, we can no longer assume that the tensions on each side of that pulley are equal, otherwise it wouldn't rotate. You need a net torque, right? T2 needs to exceed T1 for this pulley to rotate. So that means that going back to our approach here, we had to abandon the system approach, right? We had to consider the torques that were being applied to the pulley, which are from the tensions, right? Formerly, in the previous approach, the tensions were internal to our system, but now we can no longer ignore that. So we still had F equals MA, except now we have a T1 and a T2. But then also we're going to throw into the mix, we're going to throw in a little torque equals I alpha. Right? Throw a little torque equals I alpha in there. Okay? And those are counteracting torques. We actually have three equations that we need to then solve simultaneously. Okay? And we finally were able to get an expression which is similar to the expression when we ignored the pulley, right? Let me click back that quick. Okay, we have the M2 sine theta, there's the M2G sine theta minus M1G, right, over M1 plus M2. And here we have the exact same thing, except we have this extra term which incorporates the mass, essentially, the mass of the pulley, okay, or the effect of the pulley. All right, so this is the way that we solve our problems now. We take the rotational inertia, the moment of inertia of the pulley into account. I should mention that we are still making simplifying assumptions about this problem. If you just consider T1, the section of string between the pulley and M1, we are assuming that that string, and the whole string basically, is massless, right? Or that its mass is negligible compared to the rest of the blocks. Because remember, if you consider the mass of the string, there's more tension at the top because it has to support both M1 and the mass of the string under it than it is at the bottom when it just has to support M1. So we're still making some simplifying assumptions here. In this context, right, which I've spent some time setting up, in this history that we have of solving this type of problem, I'm now going to introduce how angular momentum can have you look at this problem differently and actually, in a cool way, allow you to recover the system approach. So in this previous approach here, right, we had to go back to writing F equals ma for each object, right, for m1, for m2, and then we had to write torque equals I alpha for the pulley. So angular momentum allows you to recover that system approach where you can once again ignore the forces internal to the system. In other words, what we're going to do is we are going to consider, instead of those objects separately, right, m1, m2, and I, the pulley, we're going to consider them as one system. Okay? Now we're going to apply this new equation that you learned, which is the sort of the rotational equivalent of Newton's second law his way, right? Remember, Newton's second law his way is that the external force is equal to the rate of change of momentum, right? The derivative of momentum. So this is his rotational equivalent. So we're going to apply this, and you're going to see how we're going to take a system approach to this, but we're going to end up with the same result as we did on the previous page. We're going to take the following approach. We're going to develop each side of this equation separately and then bring it together. So in other words, we're going to write an expression for the torque, and then we're going to write an expression for the angular momentum, and then take the derivative of that expression, and then combine those two expressions and solve for our unknown. So let's start with the torque. There's one slight addition to this problem here, and that is that we're going to look at this problem at a point in time, okay? At a point in time when the object is moving at a speed v, okay? You didn't really need that before. All right, we just looked at it generally because the acceleration doesn't change of the system, right? But the velocity is changing. So we're looking at this at a snapshot in time. You'll see later why that's important. Let's take a look, first of all, at the torque. Okay, remember that torque is the applied force times the lever arm, right? RF. Okay, assuming that they're perpendicular to each other, right? Technically it's R cross F. But you'll see here that the force and the lever arm are perpendicular. We have two torques, right? Or more specifically, maybe we should start with the forces. We have two forces, right? We have m1g, and then we have m2g sine theta. So write those out, right, from previously. These are the forces external to the system that are providing the torque. Okay? So when I write my torque equation, it's going to look a little different than before. Remember that the tensions are no longer external to the system, they're internal, right? So they're not providing torque to the system of 3. So when I write this, it'll be m2g sine theta, right, times r, right, r being the radius of the pulley, minus m1g r, right? So we should write in here that we're considering that it has a moment of inertia I and a radius r. Okay, so that's the torque. So let's take a look at the total angular momentum of this system of 3 objects. I'm going to pause and write out an expression. Okay, you see an expression for the 3 objects, right? Mass 1, mass 2, and the pulley. Okay, and now we're going to write those expressions. Okay, hopefully you can see that the radius r and the applied force are at right angles to each other. Okay, at the point of contact where the rope or the string meets the pulley. So we don't have any sine thetas to deal with because they come to 1. So this is going to be m1 vr, right? m2 vr, right? Because they're moving at the same speed, plus I omega. So now we have an expression for the total angular momentum, right, and the total torque. Now, what we need to do to the right expression is take its derivative, right? We need to take dl dt, okay, and then we'll be able to set the net torque equal to this expression. In this expression here, if we just look at this first one, right, m and r are constant, so we're really taking dv dt, and I think that'll be familiar to you. That is going to be a, right, linear acceleration. So we have m1 ra plus m2 ra plus I is a constant, and then d omega dt, right, the derivative of angular velocity, of course, is angular acceleration. So now we have an expression for the derivative of angular momentum with time. What I want to do now is rewrite these expressions on the next screen but bring them together under this new formula that we have. External torque equals rate of change of angular momentum. Okay, I've just simply taken the two expressions and set them equal to each other. Now our final task is to solve for the acceleration. I'm going to pause again and rewrite the equation a little differently in the next line. You can see on the right-hand side I have substituted the non-slip condition, and that gives us a nice tidy A in each of those terms, right, that we can then factor out. So the rest is algebra. I'm just going to pause again, do the algebra, and we'll take a look at the final result. Actually, I'll make an intermediate comment here. What I've done to get to this line is I've divided every term by r, which you can see that that cancels out except for on the far right where we'll get an r squared. Then on the right-hand side, I factored out the a from all of those, and you can see the final step, which is just to divide both sides by that term in front of the a. Okay, there you have it. Imagine that, the same result as we would have gotten last unit without this added approach. Nevertheless, it is a slightly more elegant approach in that you're using less equations. Okay, I'll leave it up to you whether you think this is easier than the previous approach. Remember, both are valid, just like in the olden days, right? The system approach or the individual mass approach were both valid. So you have a choice. You have another tool in your arsenal, and you can see how we apply angular momentum to problem solving.